Let's talk a little bit about amides, and they can be prepared from any other derivative. So we can use acid chlorides, we can use acid anhydrides, we can use esters to prepare amides. It's most efficient in terms of reactivity and byproducts to use acid chlorides. And we're going to use, again, two equivalents of the amine to soak up the HCl that's formed in this reaction. So we make NH4Cl, ammonium chloride. And of course, this can be an R group. That can be an R group. We can have an R group on our amine. We can even have two R groups on our amine. They don't have to be the same R group. So we can make a range of amides with different substitution patterns. Let's look at the acid-catalyzed hydrolysis of amides. So just like with any other fun with acid problem, I hope you recognize that that's what we have here. I drew sulfuric acid as the catalyst below the arrow. We're going to add water to the amide. We're going to break this CN bond, and the expected product would be a carboxylic acid. And since we're in acidic conditions, most likely we make ammonia as our product. Ammonium cation as our product, with probably hydrogen sulfate as the byproduct in this case. So let's look at this. As with any fun with acid problem, we're going to protonate first, and we can make our relatively unreactive amide into a more reactive electrophile by protonating the carbonyl. We can then add water in a nucleophilic attack. I hope that you're recognizing many of the same steps in this mechanism as we saw in the acid-catalyzed hydrolysis of esters, or even Fischer esterification. Very many of these steps are very similar. Now we need to do a proton transfer step here. I'm going to get rid of my extra hydrogen, and eventually I'm going to move it over onto the N so that I have a better leaving group. And so that arrow push made H3O+. I'm going to redraw that here. I'm going to use the lone pair on the nitrogen to grab that hydrogen. Now I have a nitrogen with 4 bonds and a cation. And I'm ready to lose the nitrogen, the NH3, as a good leaving group. So I can do this during the reforming of the carbonyl arrow push. You'll notice I'm using reversible arrows for most of these reactions. Because we're in acidic conditions, it is possible to reverse just about all of these mechanistic steps. And then the last step would be to take the relatively strong base that I just made. Amines are pretty good bases. Remove the extra hydrogen here, and I've got my products. So this is, again, mostly proton transfers with a nucleophilic attack and a loss of leaving group thrown in. So that's acid-catalyzed hydrolysis of amides. Well, let's look at the base-catalyzed. I'll use the same amide. Sodium hydroxide is the base we'll use. We're going to have to heat this reaction. We don't always indicate heat in most of these reactions, but generally we will use heat. So let's look at this. We don't have any acid present. We only have the good nucleophile, good base hydroxide. So the first step should be to attack the carbonyl carbon with the strong nucleophile. And then we're going to reform the carbonyl and kick off the leaving group NH2-. Now this is actually a very poor leaving group. NH2-, let's get the minus in there. NH2- is a very strong base. Remember that ammonia, NH3, has a pKa of around 35. And so that means that this base, the conjugate base of ammonia, is very strong. And so this step is rather uphill. It takes a bit of energy. It's probably not very fast. But what we can do as soon as we make this strong base is immediately deprotonate it using the newly formed carboxylic acid. And so what we end up with is this carboxylate plus NH3. And that means that this final step is some sort of mild acid workup to protonate my carboxylate like this to make the product. We're going to make the neutral carboxylic acid, and we did make ammonia as the byproduct. That probably is lost in the shuffle. Ammonia is a gas. If it may be protonated from our mild acid workup, that will just wash away with any water washes. So that's not really a big concern. But this is the base-catalyzed hydrolysis of amides. It's going to be the same mechanism that we saw with the base-catalyzed hydrolysis of esters. So they react under very similar conditions to esters. They're just a little slower because the amide is a more stable functional group. One last thing I want to talk about is the reduction of amides. Again, I'll draw my generic amide here. And we can reduce amides using the powerful reducing agent lithium aluminum hydride. We know that amides are very unreactive, so it makes sense that we should use the highly reactive lithium aluminum hydride. Sodium borohydride will not reduce amides, and we'll follow that up with mild acid workup. The interesting thing here, though, is that we lose the carbonyl, but we retain the CN bond. So we reduce the amide to a primary amine. So the product here is that. So that's the interesting thing about amides. We don't get an alcohol here by reducing the carbonyl. We actually get a primary amine. And so that's different than any other carboxylic acid derivative. And you should keep that in mind for future use. If we do make an amide and your desire is to make this primary amine, you could see how that might be pretty useful. So let's look at a quick example before we finish this video. Say I have this amide, and I'm going to reduce it as I showed above. Remember that we're going to basically just remove the carbonyl, and that's going to be that will be my product. So you see that this carbon became a CH2 right here. Now I have a primary amine. This could actually be used for other reactions. For instance, I could take an acid chloride here and pyridine, and I could acylate this amide, acylate the amine to get a new amide. So I started with one amide, and essentially I've reduced the carbonyl on the left side. I've added a new carbonyl species on the right side. So I made a completely new amide structure from this little two-step sequence. So reduction of amides can be a very synthetically useful technique.